Hey there. Today, we're going to dig into a rule of geometry that is so simple, you might not even notice it. But it's pretty much the secret blueprint behind everything from massive skyscrapers to the way light travels. You ready to see how a few simple lines can literally shape our world?
I mean, really think about it. Imagine you're building a huge skyscraper. You've got the first floor set, and now you're working on the 10th floor. You can't just stretch a giant ruler between them, right? So how do you know for sure that they're perfectly parallel? There has to be a foolproof way to do it.
Okay, so let's break this down with a picture. We've got three lines here, L, M, and N. Now we know for a fact that line M is parallel to line L. And we also know that line N is parallel to that same line L. So what does that tell us? Does it mean M and N have to be parallel to each other too? Well, let's find out.
Turns out, there's a name for this kind of logical connection. It's called the transitive rule. You actually see this idea all over math. And when it comes to geometry, it gives us a really elegant theorem.
And here it is, Theorem 6.6. It's so straightforward. Lines which are parallel to the same line are parallel to each other. This is the answer to our question. This is our guarantee that the first floor and the 10th floor of that building are perfectly aligned.
So, a rule is great, but how can we be 100% sure it's true? Well, in geometry, we don't just take things on faith, we prove them. And to do that, we're going to need to pull a couple of key tools from our geometry toolkit. These tools are all about understanding the relationship between lines and angles.
All right, our first tool is this line cutting across the others, the one labeled T. It's called a transversal. You can think of it like our scanner or our probe. It lets us go in and measure and compare all the different angles that get created when it crosses the other lines.
So, when that transversal line slices through, it makes a whole bunch of angles, right? Well, the ones that are in the same corner at each crossing, those are called corresponding angles. See how angle 1 and angle 2 are both in that top left spot? That makes them a pair. Same thing for angle 1 and angle 3. This little relationship right here, this is the absolute key to our proof.
And that brings us to the foundation of this whole thing, the corresponding angles axiom. Now, an axiom is just a basic rule that's so fundamental we accept it as true without needing to prove it. And this one is super powerful. If two lines are parallel, their corresponding angles are always equal. This is the bridge that connects the idea of parallel lines to the measurements of angles.
Okay, we've got our lines, we've got our tools, and we've got our fundamental rule. We are ready. So, let's walk through the proof together, step by logical step.
Let's just follow the logic here. First up, we're told line M is parallel to line L. Okay, so because of our axiom, we know angle 1 has to equal angle 2. Got it. Second, we're told line N is also parallel to line L. So again, that means angle 1 must equal angle 3. Now here comes the cool part. If angle 2 is equal to angle 1, and angle 3 is also equal to angle 1, well then it's just plain logic that angle 2 and angle 3 have to be equal to each other. And this is where we use the reverse of our axiom. It says if the corresponding angles are equal, then the lines have to be parallel. So since we just figured out that angle 2 equals angle 3, we have officially proven that line M is parallel to line N. Boom! It's that clean.
So that's the logic. And it's pretty neat, right? But let's bring this out of the abstract and into the real world. Why does any of this actually matter? Where do we see this idea at work?
Honestly, it's everywhere. You see it in the skyscrapers that shape our cities, and you see it in the simple shelves on your wall. Architects count on it to make sure buildings are safe and sound. Designers use it to create those perfectly spaced, balanced patterns. Even scientists need it to accurately draw how rays of light bend and travel. It's one of those quiet, fundamental rules that brings order and structure to our world.
Let's look at a quick example problem. Here, we're given that line AB is parallel to CD, and that line CD is parallel to EF. Well, because of the theorem we just proved, we immediately know something new. The top line, AB, has to be parallel to the bottom line, EF. And that one piece of information is the key that unlocks this entire puzzle, letting us solve for all those unknown angles. So, let's put it all together. Because we now know for a fact that AB is parallel to EF, we can go back to our corresponding angles axiom. The angle corresponding to x is given as 125 degrees. That means our unknown angle, x, must also be 125 degrees. See how that theorem we proved was the essential first step? It gave us the key we needed to solve the whole thing. So, the next time you see a building or a bookshelf or even just a cool pattern on some fabric,
Think about the simple, powerful logic that's holding it all together. It really makes you wonder, doesn't it? What other simple, elegant rules are out there quietly creating the complex and structured world we see all around us?